an increasing function, at least on an interval this is, for an increasing function, our average rate of change is positive, right? So if you can picture it, like here's our interval or something like that. If we have a function that, even if it squiggles up like that and stuff, and it's still increasing, each value is greater than the one before it, if we move left to right, then that means, well, the average, when you average everything out, that slope is positive, okay? So on the other hand, for a decreasing function, or at least on some interval, right? So for a decreasing function, we have on the opposite hand that the average rate of change is negative, okay? And then I'll just draw a little picture here to show you guys. So let's say on some interval we have decreasing in some way like that. Then when you average everything out, then we're going to get a negative slope, which means a negative average rate of change, okay? So here's some more terms to know, or at least concepts. So a local minimum, what does that mean? Local minimum just means that it's a point where a function, I'll just write f of x to represent a function, where a function changes from decreasing to increasing. Okay, so what would this look like pictorially? That would be, okay, so we have a decreasing function, okay, decreasing in some way, and then, like, let's say here's the point, here's the local minimum, and then changes to increasing. Something like that, okay? So this right here, that point there is called our local minimum, okay? Because here we have decreasing function, but then increasing function on this interval there, all right? So then we also have, of course, its opposite, which is a local maximum. So this would be a point where a function, and I'll just call it f of x for now, okay? So where a function changes, this time from increasing to decreasing. Increasing to decreasing, okay? So something like that would be, I don't know, if you had something like going up, and then it stopped, it hit its local maximum, and then started decreasing. Okay, so this is our local max, alrighty? And then just some more like terminology and everything. Local extrema, that, it's kind of a funny word, but extrema, or local extreme values of the function, that just basically includes both. So this whole term, local extrema, includes both local maximums and local minima. Yeah, so includes both. It just talks about when you have some kind of minimum or some kind of maximum at any time. Okay, so here's an example. We're going to use the cost of gasoline function. It says from the beginning of the section. We don't have to worry about that. We're going to find an interval on which the function appears to be decreasing, okay? And then we're going to estimate any local extrema using this table, all right? So let's see. So we see for each increasing t, because we always look in the direction of increasing of increase in our independent variable. So we're moving to the right. This is like left to right, right? So what we want to see is our cost, is our dependent variable, is the value of our function increasing or decreasing as we make each jump here, right? So for this first jump, we have, well, 1.47 goes up to 1.69, so we're going up. So this is increasing, okay? 1.69 to 1.94, increasing again. I'll just write I or D, okay? So this means increasing, okay? Again, we have an increasing thing, and then this is increasing, and still increasing, okay, we're still increasing. But then here, this is the important one, 3.01 to 2.14, that means we had a decrease, right? So this is decreasing. So this was the important marker here at t equals 8. That's where we switched from going from increasing to decreasing, which if you remember, when we have an increasing function and it changes to decreasing, that means right there we have a local maximum, okay? So we can write, we can identify a local maximum already. So local maximum at t is equal to 8, okay? So we have that, and then let's also write our intervals on which we're increasing and decreasing, okay? So because we started at 2, so we're going to say from 2 all the way up to 8, okay? And I always use rounded brackets here. I mean, you could use square brackets, I think either are okay, but I use rounded brackets in the sense that like for example, at the point where t equals 8, we're neither increasing nor decreasing. We're switching over. So both can't really be happening at the same time. So anyways, I always use rounded brackets, okay? So yeah, but anyways, so from the interval, this is the t interval, of course. So this is the t interval. From 2 to 8, when t goes from 2 to 8, this is increasing. The function is increasing, right? And then from 8 to 9, anyways, this interval here, we have decreasing. Okay? So this is our decreasing interval there. Alrighty? So now that we've explored rate of change and the behavior of graphs, aka like increasing or decreasing functions, now we'll go a step further, and we're going to explore a concept called concavity. Concavity, okay? Alright, and this is basically, it's kind of like the second level of analysis, I think of it as. We're basically going to be looking at, so this is looking at / considering the rate of change of, in fact, the rate of change of a function. The rate of, I can't write of change of a function, of any original function, of a function. Okay, so this might look a little bit confusing because it is. So basically, we're just trying to see, okay, how from step to step, when we look at the rate of change from point to point, how is that rate of change changing itself? Okay, so let me draw some pictures here, and we'll get a better understanding of what I mean here. Okay, so let's say we have x and y. Okay, and let's say we have some graph that looks like this. Okay, and it's kind of leveling out there. So this is example 1. So let's say, so this is increasing, right? This is an increasing function. And let's also draw another graph. So let's say something like this. So we have x and y, and this is increasing as well. Okay? But these ones look different, right? The curves look a little bit different. One's kind of pointed down or like opening downwards, and the other one, number 2, is opening up. So what's really going on here? So if we look at it, let's say we go from, we're measuring the rate of change from here. So here's 1 point, here's another, and here's another. So the rate of change from this to this is going to be this much. This, if we make equal jumps in the x, then like each of these are equal. Let's see how the rate of change is changing, right? So here's the first one. That's the first jump by this bar here. And then from here to here, we just jump this much. So it's a little bit smaller, right? And then from here to here, it's even smaller. Okay, see how the steps are getting kind of shallower, right? Because this, when we started off, it was pretty steep of a climb. And then we have like a shorter step and then even shorter. So this means that the rate of change is getting smaller, right? It's decreasing, getting smaller, we'll say. Or decreasing. So this is the case of, we have what's called concave down. Okay, it means it's kind of like opening downwards. Okay, so let's look at number 2, or graph number 2 here. On the other hand, so let's say we're measuring here, 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 and here, and like I said, they're equal intervals, or equal jumps we're making on the x, and we're just studying the rate of change. So this little one, that's a tiny little step. Okay, so it's only this tall, right? And then the next one, that one's a little bit bigger. Okay, this tall, and then this other one, that one's even bigger. Okay, then we have a jump that's like that. So the rate of change, even though it is positive, just like graph number 1, here we have the rate of change, even though it's positive, right, is getting bigger as we go along to the right, from left to right on the x, okay, is getting, we can just say bigger, okay? And this, on the other hand, is a situation, or a function that we call concave up instead, because it's kind of like facing up or opening upwards, okay? So concave up happens. Concave up is when our rate of change is increasing. Okay? Alrighty. And then concave down. I'm just defining some things here. So concave down is when our rate of change is decreasing. Alrighty. And then we have what's called a point of inflection. Kind of a fancy term, right? So point of inflection basically just means a point where a function's concavity So basically, concavity means the property of being concave up or concave down, where a function's concavity changes. Okay? So where it changes from being concave up to concave down, or concave down to concave up. All right? So let's look at some graphs now, and we'll make a little chart actually. So let's say we're describing a function. Okay, so this is increasing, this is the decreasing column. Alrighty, I'm just going to make a little chart here. And then we have concave up and concave down. Alright, let me just draw what these little like pieces of the graph should look like. Okay, so let's say we have something like this. So concave up and increasing. So concave up has to open upwards, and the rate of change is increasing. The rate of change itself is increasing as well as the function. See that? So this is concave up, and I always think like a cup, right? You want to like hold some kind of liquid in it, so it's kind of up like a cup, like half a cup in this case. And then decreasing, concave up but decreasing would be like the other half of the cup, but the function values are decreasing along with it. Okay? So that's what that looks like. And then let's go with concave down, and this is like a frown. Okay? Like a frown. Oh, the joy of rhyming words. Anyways, so concave down but increasing. So concave down but increasing would look like this. The function values have to be increasing, but it's down like a frown, kind of like that. Okay? And then concave down decreasing would look like the other side of the frown. Something like that. Okay? So these are the kind of like, I think this chart is really useful if you can recreate this either for your homework or for a test or anything like that, just right off the bat, then you really have a good understanding of what it means for a function to be increasing, decreasing, concave up, and concave down. And then you can just build from here, okay? Okay, so here's an example where we're going to study the concavity of a function. So it says, is the function described in the table below concave up or concave down? So remember how we said concavity, it studies the rate of change of the rate of change. So it's basically saying, okay, is the rate of change of our function increasing or decreasing on a certain interval? So what we have to do is actually find out what is the rate of change. So the way we do that is I'm just going to add another little row onto our table here. Okay, so rate of change is the next one. And what you do is you study between each of the points that were given from our table, how did the function change? Okay, the value of the function, that is. In this case, g of x. How did that change going from x equals 0 to x equals 5, okay? Because we're always moving left to right, okay? So from 0 to 5, our g of x went from 10,000 to 9,000. So that means our rate of change on that little mini jump there, that was negative 1,000, okay? Now let's study the next jump. From 5 to 10, from x equals 5 to x equals 10, we went from 9,000 to 7,000. So that means negative 2,000 this time. Okay? Now the next one is going to be negative 3,000. And the last one is a negative 4,000. Okay, so now that we have created this extra row, this rate of change, we can see that, okay, what is our rate of change doing as we move from left to right? And the answer would be it's becoming more negative, which means it's decreasing. Okay? So our rate of change is decreasing, which means that our graph or our function is concave down. Concave down. All right? So that's our answer. And let me just depict what this looks like actually, okay? So let's say we have a graph here. Here's our x and here's our g of x, okay? And then we'll go 2,000, 4,000, 6,000, 8,000, 10,000. So this is 10,000 all the way up here. And this is like 4,000 there, all right? And then we have, I'll just write 6,000, 8,000, okay? And then we have, let's see, we need to go up to 20. So, well, 0, 0, 5, 10, 15, 20, okay? 10 and 20. So 20, we're at 0. If I just graph the points, I'll just show you what it looks like. And then 5, we're at 9,000, so it's almost up there, but it's in the middle. 10 goes to 7,000, so something like that. And then 15 goes to 4,000, so it looks like that, right? So our graph looks something like this, which if you can rewind the video for a little bit, go back a little bit to our chart before, remember that that's the same thing as decreasing. Remember the little kind of like the segment of a graph that we drew. So decreasing and concave down. Concave down. This is what the little segment of the graph looked like, right? Okay. Alrighty, that wraps up our concepts video on rate of change and behavior of graphs. I hope that helps, and I'll talk to you in the practice problems video if you watch.